Hi guys, I'd just like to give you a lecture on elastic and inelastic collisions. So what we're going to be looking at now is we're going to be distinguishing between what an elastic and an inelastic collision is. We're going to cover what is conserved in an elastic collision, and then we're going to talk about, are any collisions actually ever elastic? So, just a quick recap on what we've looked at before. For a system of interacting objects, the total momentum of the system remains constant providing there's no external forces. So essentially what that means is, providing no external forces, the sum of the momentum before in brackets before equals the sum of the momentum after. Cool. I just put a couple of diagrams in here, a couple of cars here. Had a bit of an accident. Just to remind us that, you know, things with a lot of momentum you don't want to get in the way of. And also these rugby players here, again for the same reason, things with a lot of momentum you don't want to get in the way of them. I did just want to very quickly do an example with you. It's one of the textbook questions that you should have done last week. A rail wagon of mass 5,000 kilograms moving at a velocity of 1.6 meters per second collides with a stationary wagon of mass 3,000 kilograms. After the collision, the 3,000 kilogram wagon moves away at a velocity of 1.5 meters per second. Calculate the speed and direction of the 5,000 kilogram wagon after the collision. Well, that's an absolute mouthful, but the way that I like to approach these is as follows. So I would draw a before picture where we've got a 5,000 kilogram wagon. And that's going at 1.6. And we've got a 3,000 kilogram. That's going at nothing. And then after, our 5,001, we're not sure, and our 3,001 is going at 1.5. That's what that question says, and it's all put in a diagram. So using our sum of momentum before equals sum of after. So sum, now P stands for momentum. So sum of momentum before equals sum of momentum afterwards. So what is it before? Well, we've got 5,000 times 1.6 plus 3,000 times 0 for before, and that must equal 5,000 V plus 1.5 times 3,000. There's our equation. This term is 0, so let's do 5,000 times 1.6. That's 8,000. So we know that 8,000 must equal 5,000 V plus 4,500, which is 1.5 times 3,000. Subtracting 4,500, we get 3,500 equals 5,000 V. Therefore, V equals 3,500 over 5,000, which is 0.7. And because it's positive, it's going in exactly the same direction as before. So we can go ahead and we can take, oh dear, we can take away that question mark and put the answer in as 0.7 meters per second. And you are happy with that? We've done that before. Just a quick recap there. Now, I need to talk about these terms elastic and inelastic collision. Now, in an elastic collision, it's where there is no loss of kinetic energy. So it's a key term in here. elastic and kinetic energy. Elastic collision is where there is no loss of kinetic energy. So the sum of kinetic energies before the interaction will be the same as after the interaction. And an inelastic collision, so key word here, inelastic, is where the loss of kinetic energy, is where there is a loss of kinetic energy. Is where it should be there. Is where there is a loss of kinetic energy. The sum of the kinetic energy before a collision would be greater than the sum of the K after the collision. So basically, elastic is where it's absolutely perfect. There is no loss of kinetic energy, and an inelastic is where it's not. And the way I remember that is by a bouncy ball. Bouncy balls are kind of elastic, and a bouncy ball will always come up to the same point at which you drop it if it's elastic. So, bouncy balls, obviously, if you were to drop a bouncy ball onto like a stone floor or a hard floor, they do not bounce up to the same height in reality. And the reason they don't do that is because it's not an elastic collision. If they bounce back to the same height, then the collision would be elastic. So far, we have distinguished between elastic and elastic collisions. And you know what is conserved in an elastic collision. Are any collisions really ever elastic? Well, what would it need to be completely elastic? Well, energy would need to be completely conserved through the kinetic amount. Now, if you can show me any collision where there's no heat or sound, then yes, it would be elastic. But if anything collides, you're going to hear it. There's going to be some friction there, surely. Anyway, I just wanted to give you a couple of examples here. If the car collisions at very low speeds, car collisions at low speeds are very nearly elastic because there's little friction and little sound. Providing there's no damage. Otherwise, some of that initial kinetic energy will go into making the damage. If the cars couple or stick together, though, and move off as one, then the collision is definitely inelastic. I just want to go through a quick example with you. So, we've got a railway wagon of mass 8,000 kilograms moving at 3 meters per second, and it collides with an initially stationary wagon of mass 5,000, and the two wagons separate after the collision, and the 8,000 wagon moves at a speed of 1 meters per second without change of direction after the collision. So, A, we've got to work out the speed and direction of the 5,000 wagon after the collision. So we'll do that first. We're happy to do that. We know how to do it. So, I want my before diagram. What have we got? We've got an 8,000 moving at 3 meters per second. Oh, that's 30, Steve. 3 meters per second. Initially stationary of mass 5,000. And our after picture, we've got the 8,001 moving at a speed of 1 meters per second without change of direction. Good, so it's not minus. Otherwise it'd be the other way. That's 8,000. And we've got this one here, that's BV, and 5,000 here. So let's just go ahead and work it out. So sum of momentum is before and after. So what's our sum of momentum for the top one? Well, we've got 8,000 times 3 plus 0, essentially. So that's just 24,000 for the top. And for the bottom, we've got 8,000 times 1 this time. Added to 5,000 V. So we've got 24,000 equals 8,000 plus 5,000 V, so 16,000 equals 5,000 V, so V equals 3.2 meters per second. So we can just go ahead and write that on. So that's part A done. Now, part B, the loss of kinetic energy. So we know straight away that because of the loss, it is inelastic. But we can go ahead and work out that loss. So let's look at again the before picture. I'm not going to draw a diagram again, but before I'm just going to I'm just going to do the kinetic energy. So before, just in brackets down here, we know that kinetic energy is a half mv squared. Just in brackets there. So before, what have we got? We've got 8,000, so we've got a half times 8,000 times v squared added to the other one, which is a half times 5,000 times 0 squared. And then after, we've got a half times 8,000 times 1 squared. And then for the other one, we've got a half times 5,000 times whatever our answer was up here, 3.2 squared. So if I just go ahead and work out the top one, so 0.5 times 8,000 times 9, that's 36,000, because the other one's 0, so top one is 36,000. Obviously that's joules, and 0.5 times 8,000 times 1 squared. Yeah, I don't know why I need to calculate for that. 4,000 for this one. And 0.5 times 5,000 times 3.2 squared. 25,600. So we can see that the loss of kinetic energy is just going to be 36,000, which is what it was at the start, take away what it was at the end. 4,000 plus 25,600. It's 6,400 joules. That's the final answer. So, hopefully you've learnt what an inelastic and elastic collisions are, what is conserved in an elastic collision, and are any collisions really ever elastic? And the answer is, in reality, no, because you are never going to get a collision with absolutely no friction or no sound or anything like that. Okay, cheers guys.